Thank you so much. Good morning, everybody. I'm Greg. I'm the creator of Leptos, among many other things. I don't know if Ben is in here. If you see him around, he has lots of stickers. Despite the fact that we have lots of stickers, and I have a Leptos t-shirt on underneath this shirt, Leptos is not like a startup or anything. It's old school community open source project that we all built together for fun. So you are very much invited to get involved. And don't worry, I am literally not trying to sell you anything ever, including during this talk. So I want to give a kind of, try to be as balanced as I can in talking about the place of Rust in building web applications. But I'm not here to talk about Ben, I'm not here to talk about Leptos, I'm here to talk about the future of Rust web applications. So what I want to do this morning is to talk about the future. I want to go back a little bit and talk about the past, talk about how the web got to the place that it is today in terms of application development, in terms of the patterns and the architectures that we use for building front-end UIs. I want to say a few words about the present state of Rust and WebAssembly frameworks. I want to highlight some of the issues that we currently have, some of the limitations in the current models that we have, and then I want to spend some time talking about the near future, the ways that people are addressing those various issues and problems and limitations. And I'll do a bunch of demos during this part of the talk. So we'll have some slides up front, a bunch of demos, and I want to leave plenty of time for Q&A. Anyone who's ever seen one of our online meetups knows that I can go for about an hour and a half on Q&A alone, so I'll try to reel it in, but I do want to leave some time for questions at the end. I'm really not assuming that you know much about the topic. If you have used one of these frameworks, or if you're a seasoned front-end web dev, at parts you may be saying, okay, get on with it, but we're going to tie everything back. The issues and the demos that I'm going to show toward the end about the future end up tying back to these parts about the past that come up at the front. So I really want to ask the question today, is there a future for interactive web applications that are written entirely in Rust? I also want to say a note about what I am not talking about today. So when I talk about Rust on the web, I am not talking about building web infrastructure using Rust, so the kind of work people are doing at AWS or Cloudflare. I'm not talking about building API services in Rust, so I'm not talking about spinning up Axum or Actix or PubX or Loco, or there are some people walking around with t-shirts that say, we're building an awesome web framework at cot.rs or something, right? I'm not talking about any of those things. And I'm not talking about building tooling for web applications using Rust. So there's a huge amount of work going on right now in the JavaScript ecosystem and even in CSS in rebuilding tooling for web applications using Rust. I'm not talking about any of those things today. And the reason I'm not talking about them is that I actually think it's almost taken for granted that they're good. So sometimes when everyone agrees that something is a really good idea, there are great talks to be done about it. But not only do I know very little about any of those things, I think they're great. And I'm going to talk about something else that people are not always convinced is a good idea. So if you leave this thinking, I don't want to use foul language about myself. If you leave this thinking, I don't know what I'm doing or I'm making wrong decisions, that's totally fine too, right? So what I am talking about is using Rust to build interactive web applications, meaning your server sends down some amount of HTML, it loads some amount of JavaScript and WebAssembly, which we'll talk about, and then the user can interact directly with that page, and it does some combination of stuff happening right there in the browser for interactivity and going back to the server for data and so on. So the kinds of things I'm talking about are these JavaScript frameworks, React, Vue, Angular, Svelte, Solid, and the work that I do is in the Rust equivalents to those frameworks. So things like Vue, Leptos, Dioxus, Sycamore. If you are here for something else, I will not be offended if you leave. Genuinely, it's okay if this stuff does not float your boat, right? So I'm just curious, who has used one of these JavaScript frameworks on the left or uses it regularly? Beautiful. Okay, so we have a lot of kind of front-end people or some familiarity. Who has used one of the Rust frameworks over there on the right? Cool. That's awesome. Great. So wonderful to have you all here, and get ready. So one of the questions that comes up all the time in this is, but why? Why would you want to do this? Why would you want to use Rust, this notoriously finicky systems programming language with a borrow checker and like a sea urchin protecting you from evil, right? Why would you want to use this to build a web application? And to answer that question, that's where I want to start to go back to the past, and back to what I call almost the dream of the web. So we're actually going to play a guessing game here. It's going to be a fill in the blank. This is a user testimonial of kinds. This user says, if you want to write a web app, you can use anything. I mean, you can literally use any programming language that's ever been invented in the history of time to create your web application. That's amazing. And people don't always recognize that for the gift that it is. I think JavaScript is a fine language. It's not a horrible language. It's not a great language for me. Anyone ever had this feeling? Right? My personal truth there, fill in the blank, best programming language ever made for me. Does anyone have any guesses? Somebody said Lisp, which is actually on a very good track. You're thinking, Perl? I like these. Okay, I'm gonna give you a hint. We're at a conference called Rust Nation, right? I'm giving you one of the letters, all right? Any guesses?
Ruby.
We're getting closer. Ruby! It's a quote from DHH, creator of Ruby on Rails, right? I love this quotation. He is so enthusiastic about the diversity of languages that the web supports, and I think this is a really important point. In a lot of ways, Ruby and Rust could not be more different from one another. Ruby is this interpreted, very dynamic, very object-oriented language. Rust is not those things. And yet there's a real similarity in the elements of focusing on developer happiness, this sense of joy, this sense of a community of people united around loving and enjoying using a particular language and having a really pleasant experience doing it. And so as different as Ruby and Rust are, there are some real similarities. And he's absolutely right about this being an element of the web, and it always has been. So I want to do a little bit of a history tour now and talk about what it is that makes the web so good for promoting the diversity of different programming languages. So this step one, this is a very traditional outline of a web application. You might call it a multi-page app. So you have a client, and you have a server. And the client makes requests to the server by fetching different URLs from the address bar or links or forms, right? And the server responds with HTML and CSS and a little bit of JavaScript just to add that interactivity, right? Just a little bit of JavaScript. Except the thing is, this user experience is not actually that amazing. Constant requests from the browser back to the server take a little bit of time. If you've ever used a kind of 90s or early 2000s web application that's constantly going back to the server, that's working only through forms, you may have had this experience. If you're using some web app that you might use today, for example, a calendar application, and every time you wanted to move something on the calendar, you needed to press submit and reload the page, and browsers before the last few years would unload the page and then reload the page, so you get this flash of white in between. It's actually not a great experience, as opposed to, what if we add just a little bit of JavaScript so that when you move the item in the calendar, it just moves, right? That would be cool. But the benefit of this is that on that server, you can be running whatever you want. It can be C or Perl, all those CGI bin applications. It could be Python or PHP. It could be Java or Ruby or Rust. You can choose the language that works for the problem that you're working on, as long as you're sending HTTP responses with HTML and CSS and a little bit of JavaScript. You can be running any language on the server, and that's the beauty of that diversity of languages that DHH is talking about there. But so we add our little bit of JavaScript. You get this kind of MPA plus jQuery model, right? Where you have this original loop of returning some HTML coming from your server in whatever language, and then you're adding some imperative JavaScript so that when you move that calendar item, the calendar item just moves, right? And then you can submit it and make the change whenever you want. And you get into this faster kind of loop between the client and some client-side JavaScript. But there's a problem with this kind of model, which is essentially that mixing a server that's sending down some HTML through a templating language and then some imperative JavaScript that's making changes to it, it's very easy to get yourself into a kind of imperative UI spaghetti code goop architecture, you might call it. Where it's very hard to keep track of what's actually supposed to be on the screen. You may have written applications like this yourself. Once you get above a certain level of interactivity, it doesn't really scale very well. And the other problem is that you end up duplicating a lot of your code. For example, in the calendar, right, you might have a template to render a calendar event on the server to HTML. And then you say, ooh, but we want to be able to create one and just show it in the calendar on the client. Now you have to create a template to show a calendar event in JavaScript too. And now you're maintaining the same code for the same UI in two different languages in two different places. It's not a great model. And so over time, people move toward what we would call single-page apps, where much more of that UI logic is just done in JavaScript in the browser. And so you end up sending actually much less HTML and CSS at first, much more JavaScript, and then you are almost entirely in this tight loop between the user and this JavaScript running in the browser. And when you want to go to the server, you tend not to do a full page reload, but you go for JSON and you get JSON back, right? Many people who have written web apps have written something like this in the last 10 years, right? This is almost the default mode. And of course, there are some problems with this as well, namely, your SEO isn't as good because not all search engines will run JavaScript for you. And if the content of your page is just an empty body tag with some JavaScript, it's not obvious that every search engine likes that. They may penalize you. But also, if you try to do something like paste that into a social media site, you may find that thumbnails or descriptions don't come through because your meta tags are only being rendered by JavaScript in the browser. This is a very common problem. And so all of these frameworks added server-side rendering. So now you can once again respond with this nice actual HTML from the server of the initial page load, and then you get into this tight loop in the client. So the interactivity is there, and it's a nice experience. It can be a nice experience if done well, right? We'll all grant that it's possible to create a bad web application this way. Only there's a problem here, which is that it actually starts to affect the diversity of the web. I don't know if anyone has seen this happen in code bases or projects that you've worked on. It's obviously very possible to write API services in any language, right? That's not a question. But when you get to creating the UI, you end up actually pushing more and more JavaScript onto the server when you're in a server rendering model, because you just want to be able to write your code once and render it on the server and then hydrate it in the client, right? And so you end up with a model of the web that looks less like this and a little bit more like this, where JavaScript is running everywhere. And again, that's fine. JavaScript is fine. But is it possible that there's another way? Yes, of course, there is, because it's not actually the case that you can only respond in 2025 with HTML and CSS and a little bit of JavaScript. There is, in fact, a secret fourth thing, which is WASM, WebAssembly, the fourth programming language that browsers can run, right? It's kind of a programming language. It's mostly a compile target for other programming languages. And so what that means is that instead of JavaScript, you can run WASM in the browser here. You can have, say, Rust or another language running on your server, and you can compile that same Rust code to WebAssembly to run in the browser. And so just as wanting JavaScript for interactivity in the browser ends up pushing JavaScript onto the server, you can use whatever language you want within some bounds of what actually compiles to WebAssembly on the server, right? You can run a native Rust binary on the server and then compile to WebAssembly to run in the browser. And that's how these frameworks work. This is what you would do with Leptos, with Dioxus, full stack. You can do it in U. You can do it in any of these Rust front-end frameworks. And of course, the point of that is just to be able to restore some of that diversity of the web. There's a big table here. I accidentally deleted all those slides with the animations, and I made it into a table instead. And then I decided I didn't like that. So if you want to go back and look at the slides at some point, this is everything I just said in text. So WebAssembly, right? People use WebAssembly in a lot of different ways. There's another talk about WebAssembly today that almost doesn't overlap with what I'm talking about right now, because WebAssembly can be used as a performance optimization for doing number crunching in the browser. It's a better thing to compile math to than JavaScript. It can be used as a sandbox. You can run it on the server and use the same kind of sandboxing that browsers do for applications to get some benefits using it on the server or for plugins. Or you can just think of it as a compile target, something Rust can compile to that can run in the browser. You cannot compile Rust to JavaScript and run it in the browser. Or you can, and it's horrible, right? So that's what WebAssembly is for, is compiled languages being able to have a compile target that runs in the browser. And we are really mostly here for purpose number 3 of WASM, not for WASM in the whole. But again, we get back to this question of why. Why would I do this? Why should I build a web application in Rust? People ask this a lot. And I would encourage you just not to think in terms of that question. I would say if you're asking, why should I build a web application in Rust when TypeScript is so great? Don't. Stick with TypeScript, right? But if you're thinking, I have this code I've written in Rust, I have this library I want to use, I really enjoy this language, I'm at a conference called Rust Nation, I like Rust, I'm assuming that's true for many of you. Can I build a web application like this? The answer is yes. And there are lots of good reasons you might want to. So if you want it to be relatively tightly coupled to some kind of a Rust backend, if you want to be able to share code and share types between your server and your client, Maybe you're in a situation where you have some business logic that's written in Rust, and you want to use that as a library for native apps and mobile apps, and you want to be able to run it in a desktop application, and you want to be able to run it on the server, but you also have situations where you want to actually run that in the browser, right? That's a great reason to do this. And another good reason is just that Rust is a really nice language for modeling certain relatively complex domains. It's a silly example, but a couple of weeks ago, I was making a little math game for my 7-year-old who's learning arithmetic. I wanted to do some practice for addition and subtraction. It's just nice to create an enum of problem and then have addition and have it have some fields, and subtraction and have it have some fields. I would rather do that in Rust with the tools that it gives me than I would in JavaScript, right? And I can. It took me like an hour, and it's a nice little app. So I want to talk about the present. How do I do that when I sit down to create an application? The kind of foundational crates at the core of all of this are WASM bindgen and WebSys. So WASM bindgen is a crate and a CLI tool for generating bindings to WASM, hence the name, from JavaScript. It allows you to call out to JavaScript functions from WebAssembly and into WebAssembly from JavaScript, meaning you can write Rust code that calls any of the browser's APIs, just like you can call them in JavaScript. And then WebSys actually generates those bindings for all of the web APIs and DOM APIs. So you yourself personally don't need to do any of the work to bind to or call out to browser APIs. You can just use WebSys, and you can have typed access to all of these functions. So for example, if you would ordinarily call a function in JavaScript and you say, does this throw? I don't know. Maybe I can find it in the docs somewhere. WebSys is going to return you a result, which is nice, right? That's actually kind of handy. Who's ever written a JavaScript function that you didn't know could throw an exception and it did? In prod. Good, good. I see you, and I love you. All right, so a few of the frameworks. U is kind of the OG. It's the first really big and mainstream front-end framework in Rust. It's very stable, very mature, relatively slow release cycle at this point. And if you look at the code, you can see this looks kind of like you might imagine React code would look if you wrote it in Rust. It has a function component. There's a use state. There are 2 callbacks to increment and decrement the counter. Can I move my mouse? Good, yeah. And then there's this kind of JSX-looking HTML macro. And you'll see, I'll go through the other kind of frameworks here, but they're all kind of like this. It's these declarative front-end framework styles, components, some kind of state, some kind of view. This is a little example of Leptos. Leptos takes a kind of non-React-like approach. If you're familiar with JavaScript world, it's more like Solid.js or Svelte 5, where it's using signals to do fine-grained reactivity, which means with Vue or React, when this state changes, it's going to rerun the whole component, create a new virtual DOM, diff it against the old virtual DOM, and then say, the count went up by 1. None of this other stuff changed. Well, it turns out when you have a compiler, right, you can actually say, we know that none of this is ever going to change except the count, and you can have a set of runtime signals that it just updates that one text node. It's very actively developed. Ben has merged 75 PRs in the 2 days I was on an airplane getting here. And we really, I think, focus on web standards and progressive enhancement. So Leptos really is a web framework. It's designed for the core functionality to work with no WebAssembly support, with no JavaScript in the browser, and to build on these core kind of HTML and web primitives and go from there. If you hate macros, by the way, here's the non-macro builder syntax version. Never say, oh no, they forced you to use all these macros, I'll cry. Dioxus is another really interesting framework. Dioxus is kind of React-like, but it's been moving away from React patterns. The thing I think is most interesting about Dioxus, some of you may have heard of, is they're very focused on a desktop app development and also mobile app development, using web technologies to build more native-seeming GUI apps. And they have this wonderful, almost inverted Tori model, if you've ever heard of Tori. So you have Rust code. If you have a Dioxus desktop app, you have Rust code running natively that's then sending commands over to a web view. So the actual rendering is done by an embedded web view, like a little browser in your application, but your actual application code is running in Rust in a native binary. Very cool. It's not just running in the browser. It's a great, we love Dioxus. And then Sycamore is another framework. Sycamore is in less use now, but Sycamore and Leptos and Dioxus have all kind of mutually inspired one another over time. It's a little bit of a slower release cycle, but it's a really, really solid framework if you don't like the other options here. So what's the state of Rust web applications? What can you do with these 4 or 5 frameworks I've just listed? I was honestly trying to think of a way to summarize that, and I think all that I can say is anything you can do, I can do also. There is not some magic killer feature to Rust web applications. You can't create an application with any of these frameworks that you could not create with a JavaScript framework. There's almost nothing that you could create with a JavaScript framework that you couldn't also create with one of these frameworks. The difference isn't really in the feature set. Obviously, between different frameworks and libraries, there are different features that are or aren't there. But the real difference between them is just what language you're writing things in, right? And so just to pull a bunch of random examples off of the awesome Leptos repository or out of other people's talks, if you all know Chris Biscardi, his Rust Adventure website is built in this. So the sort of portal for his Rust learning platform is all built with Leptos. So you can build, an education portal. You can build something for hiring people in a kind of HR and employment way. You can build a distributed federated wiki. You can build an e-commerce site. You can build anything that you can build with any web application, right? Doing demos of actual sites is boring because they just look like normal web applications. There's nothing interesting to your users, and that's probably good. There are some limitations, though, and so I want to get into these current limitations. I'm going to briefly mention them, and then what I'm going to do is walk through each one of the limitations and do some demos of the current work that's trying to address these problems. And then we'll do some time for Q&A at the end. So what are the limitations of using Rust for web applications right now? One is compile times. We all know it, right? There's interesting work that you can do, but this is a Rust conference. It's a safe space to talk about compile times. Number two is binary sizes, and I'll say a little more about why that's a limitation. And number three is my least favorite word, ecosystem. So we're gonna look into these all a little and talk some about the future of Rust web applications. So first up is compile times. It's probably obvious what I mean by that, but essentially the Rust code is notorious for producing really fast code relatively slowly. If you compare it to any number of other compiled languages, Rust has really good compiled output, but isn't the zippiest for incremental changes, right? This doesn't always fit really well with UI, because when you're building a UI, what you actually often care about is a fast iteration loop, something being shown in response to changes that you're making, but not necessarily the raw speed of the code. If you're writing an application where you click a button and it submits a form, like the fact that you didn't need to allocate a hash map to stick the form fields in doesn't really matter relative to your making an HTTP request. But the fact that it took you 5 seconds to make that change might actually matter to you more. So one of the solutions to this kind of problem is something that we end up calling hot reloading. And Dioxus and Leptos have both done a lot of work on this. I'm going to give you a Leptos example because I know it better. But to be honest, shout out to Dioxus. They've actually done more interesting work, and I'll say a few words about that too. By the way, if you have a relationship with the demo gods, I ask you now to call upon their names. Let me close this one here. And I also apologize if I start using any Vim key bindings here. My VS Code color scheme is a little more readable. So this is, of course, a very common situation in web development. You have spent 6 months trying to create an example with some buttons using Tailwind, and then you found there was an example already. You have accidentally loaded the wrong version of the page, and then you refresh it. Good, and we've got blue buttons, right? And so then your boss comes in and says to you, there's actually a problem here. There is actually a problem here. There we go. Okay, there's actually a problem here, right? We need these buttons to be orange. And you say, shoot, I wrote this app in Rust. We want to try out some different colors. I'm going to have to recompile this thing, right? And recompiling things isn't always bad. I actually forgot to show you the slide with one of my favorite XKCD comics, right? Which is compiling, and they've got the sword fighting going on, right? Developers' favorite thing is best excuse for slacking off. My code's compiling. So they say, okay, we have some blue code. Of course, if you we're gonna, am I bumping my? There we go. So we're going to update this to orange or whatever. So we're going to find blue and replace it with orange, and that's relatively easy. And then we're going to get ready to compile, right? And okay, on guard. Wait, I wanted to sword fight. Okay, so obviously these guys have just implemented some special behavior for adding Tailwind classes to something, right? Like anybody could do this fine. Once you learn that Tailwind, people are shipping all these classes in their actual application code, makes sense to create some optimizations. But obviously, this isn't a general purpose thing. So this will need to compile, right? We're adding some Rust code here. This is actually going to run. So now at least we've got like a good chance to, what? Come on. It's like, and then you just quit, right? So there are obviously, this isn't a perfect solution, right? But what are we doing here? This is a strategy that I call compiling faster by compiling slower, making the compiler do a little more work in order to look like it's doing less work. So all that this does, right, we've got this view macro. The reason we've got this view macro is that a lot of people find it convenient to write their HTML-like stuff in an HTML-like syntax. But once you've got a macro, you might start looking at it and saying, well, in order to update these things on the screen, we don't actually need to compile a bunch of Rust code. To make changes to something, we just need to look at this macro, which is an HTML-like syntax, parse the old one, parse the new one, say what changed, and then send something over a WebSocket to just update it, right? So this kind of hot reloading just works on the static parts of templates. It just lets you tweak something and have the changes appear instantly. But when you're in that tight kind of iteration loop of tweaking markup or tweaking styling, right, it can be really useful. And of course, if you're using actual CSS, it's really easy to do because you can just edit a CSS file and we can just send the new CSS file over if you're not actually touching the Rust code. So I always like to use CSS, but I know that a lot of people use things like Tailwind instead. So like I said, Dioxus has some even more interesting hot reloading work that they've been doing. John Kelly from Dioxus has been doing work on what he calls in-place Rust binary patching, which is you have a running Rust binary, right? Dioxus is going to spawn a window for you in a desktop application. And if you've ever used Cargo Watch with a GUI thing, when it recompiles, right, it will kill the window and reopen the window, and you lose whatever state you had. So he's been working on how can you actually do some analysis, almost dynamic linking, and replace bits of the application while it's running. And he has demos working for server-side applications too. So there's really interesting work that's happening here. A lot of it's not done by me, but these little incremental things that we can do to basically skip compiling parts of the application when you make changes that don't actually need the full strength of the Rust compiler doing its amazing work, that don't need LLVM doing its amazing work to make your code fast, where you just want to see things quickly on the screen. There's also a lot of work being done by amazing people on the Rust compiler itself to continually improve the compile times, of course. And then I do lots of amazing work to continually make our compile times worse by doing clever things with generics. And then we try to fix those things, and we pat ourselves on the back for fixing the problems that I introduce. So the second problem that I want to talk about, see, we missed the comic. The second thing I want to talk about is those binary sizes, right? So what makes binary sizes a problem? The real issue is kind of twofold. One is that if you think about it, when you write JavaScript, you are actually shipping a huge amount of code to the client. It's just that they already have it because it's installed in their browser. So the whole standard library, the whole language runtime exists in the browser. When you ship some Rust code compiled to WebAssembly to your users, the bits of the standard library that you're using are compiled into the WASM file that you send them. You don't get any of the benefit of sharing that across applications. And of course, another downside, right, is that the Rust compiler is built for monomorphization, right? If you have a generic function, it makes a different copy of that for every type, which makes for fast, big binaries. And the actual performance characteristics of web applications are different from a native application where you install something. Sure, it's a few megabytes. It can be dozens, hundreds of megabytes, but it's installed and it runs. Well, web application, you're constantly shipping things to people. And this is one of the great things about the web platform, right? It's decentralized. It's constantly, you constantly receive the freshest version of an application, right? But it also means that there are some important characteristics of the program that depend on things like binary sizes, bundle sizes. And the key one is time to interactive, right? That means the time between essentially when you type in the URL and when you're able to interact meaningfully with the page. And the more JavaScript somebody has to download and run, or the more WebAssembly that has to be downloaded and run, the slower that is. And especially for things like e-commerce, right? You've seen companies like Amazon have never moved over to a JavaScript framework because the amount of JavaScript you need to ship to use any of them is so large that it would cost them millions of dollars just in terms of the cumulative milliseconds of extra time for people to be able to add things to their cart. So how do you achieve these sweet 100s on your Lighthouse score, in other words, right? And I'll actually say this is just the Leptos homepage. It doesn't use any of these techniques, so you can get perfectly nice performance scores without using the things I'm about to say as well. But so one way that you can do this is by thinking about how can you shrink down the overall size of your application? And the other way is by thinking about how you can spread that out over time so that you don't all have to load it all initially. It's important to say off the bat, by the way, that a kilobyte of WebAssembly and a kilobyte of JavaScript do not cost the same thing to your browser. JavaScript is an interpreted language, right? It has to be downloaded, parsed as a whole block, and then executed. WebAssembly is designed for streaming compilation out of its bytecode into native code. And in fact, Mozilla engineers will post articles like, hey, we can actually compile WebAssembly as fast as it comes in over a typical internet connection. So on a lower powered mobile device, we can still compile about as fast as your cell network can download the data. And on a desktop device, we can compile about as fast as your Wi-Fi can download it for you. And of course, my favorite part about this article is that this was posted in January 2018. So they were saying this 7 years ago. This was the state of Mozilla's browser. It's essentially the cost of running WebAssembly is the cost of downloading it. And a WebAssembly app could range into, let's say, the low megabytes, right? But a very basic, minimal hello world type of thing could be in the dozens of kilobytes. Downloading a few dozen kilobytes or a few hundred kilobytes is not actually that big of a cost. So I do want to start out by saying that. And yet I will be showing you things and be like, I got this from 38 down to 35 KB, right? And that's really exciting too. So the problem here is essentially that in that server-side rendered and hydrated model that we showed, version number 4 and 5 in that history, where you're sending actual HTML, including actual markup and data so that your SEO is good, and then you're hydrating the whole page so that you can be interactive with it. What you have to do is to run that whole application on the server, and then run it again on the client. You have to ship the code for the whole application to the browser so that not only can it add the right kinds of interactivity, things like event listeners and so on, but also then when you navigate to the next page, it can render that in the client without going back to the server to fetch the page again, right? So you end up shipping the code for the whole application. The problem is that your time to interactive then becomes proportional to the amount of content on the page. So just adding more content on the page, even if none of it is interactive, makes it slower to load and slower to begin to interact with. So one solution to this is instead of doing full hydration, where you hydrate the full page, to do something called partial hydration, which is sometimes called islands. And the islands metaphor comes from this. Imagine you have a sea of inert HTML that gets sent down from the server. It doesn't have any interactivity beyond the basic stuff of links and forms and so on. You then hydrate it, and you fill it in with a whole area of land, which is the interactive part. I'm willing to grant that you are hydrating something by taking away all the water in this metaphor. I apologize. It's not my metaphor. So islands do something different, right? You have this sea of HTML that comes down from the server, and then instead of filling in the entire thing with landfill like they did to make my beloved city of Boston, you only hydrate these little islands of interactivity. So if you imagine this is, for example, a social media application, right? The outer shell there looks the same every time you go to it. That can just be HTML rendered on the server. There's no interactivity. It's a header with a banner and so on. Up there in the top corner, maybe that's a profile picture that you click something and it pops up a little modal. Okay. And then this inner blue, right, that's all the posts. On the first load, those can be rendered on the server. You'll see, I'll have a little demo of Hacker News, right? That people's comments can just be rendered on the server. And then maybe you have a little, those inner squares, you have a little like button, a little repost button or something. You want those to be interactive on the client without doing like a form request to the server. And then that outer green thing, these are not only islands, they can be like atolls, right? So you can have outer server content and inner server content, and around it you could have maybe, this could be a tab selector. Which of these three things from the server do I want to show, right? And the important thing about this is the amount of WebAssembly that you're shipping to the user's browser is the size of the green. Small is good, right? So when you have full hydration, you're sending the full page. When you have partial hydration, you're sending part of the page, and so it's smaller. And what we see in reality, I think in most migrations to this, is you get something like, depending on the application, something like a 75% reduction in the size, which all else being equal is like a 4 times improvement in that loading time, right? Obviously, it's blocked by things like CSS and images and so on, but it's a big improvement. You can reduce a lot of that code just by switching over to only using islands for the interactive stuff. So I want to show a little demo of a couple of examples of islands here. So this first one is the Hacker News example I mentioned. I have to say I actually like this better than the actual Hacker News UI. I didn't create this example, I just ported it. But if you navigate through the pages, and I'm appreciating the speed of the Wi-Fi here too, because it shows exactly right, you'll notice you have these normal page navigations. But then once I go here into comments, right, you have this interactivity that you would expect to toggle the comments. This whole application is only shipping 44 kilobytes of WebAssembly. So in other words, that's fewer kilobytes than a React hello world, right, is this application. So that's not bad, right, especially given that a kilobyte of WASM is cheaper than a kilobyte of JavaScript. This is fine. This is great. It's not the best user experience, right? You still do get that kind of server reload effect. It's a multi-page app plus jQuery, except it's entirely declarative, right? So it uses these kind of declarative, almost functional paradigms out of web frameworks. You don't have to write the code to manually imperatively update this stuff. It's just doing it for you, which makes it much more maintainable. But wouldn't it be nice if we could get that same interactive experience while still having the benefit of islands? And yes, it would be nice. So look at this, imaginary contact app with some fake data of people with very interesting names. If I have this, right, and say I want to search for a user, say I want to search for Ben, is there a Ben in here? Okay, we have all of our different Bens. I can, copy, imagine this was to add people to a group, right? And then imagine, oh no, I actually don't want them, and I'm going to delete this person. I can go to details, I can go to this about page. I can click this counter button because it wouldn't be a framework demo without a counter button, right? Oh my gosh, I need another button. Yeah, it's minus equal 1, not plus equal 1. Oh, that would be really nice. Yeah, we can. Is there a right-click event? Don't distract me. Sorry. We're gonna go way off track. I'm like MDN docs, right-click. Okay. So this one also just ships like 43 kilobytes of WebAssembly, but it has a slightly nicer feel. Who thinks that the feel of this one is a little nicer than the Hacker News one? Genuine question. You don't have to agree with me, but I kind of think it's a nice little animated search thing, whatever. So what this is actually doing is it is still using islands mode, and then it's adding a little bit of client-side routing on top of it. If any of you have ever used Astro, who's used Astro? Who's heard of Astro? Who's heard of the View Transition API? Beautiful. So there's an API in the browser, right, that can animate view transitions like this. It's only supported in Chrome, of course. Everyone else will come along eventually. But you can essentially add little animations like this, which is what I'm doing here. And this is just being done automatically. So on every request, this list is not interactive on the client. There's no client-side interactivity in this list. There's no WebAssembly running in the browser that's doing anything having to do with this list when this changes. What it's actually doing is going and making a little fetch back to the server and getting new HTML, and then using the fact that in Leptos in particular, we have this statically typed view tree, so it can do a very smart little diff and replace, maintain some client-side state like these checkboxes and so on. It looks like it's running in the browser. And in situations where you're going to be loading data from the server anyway, this can be a really nice option. So this is one of the things that I've sort of been working on over the last few months that needed a lot of work that happened over the year before it to actually work well, where you can end up shipping a very small amount of that client-side WebAssembly to a user, but still actually have a pretty nice interactive experience. So that's one way of reducing this binary size problem, is to shrink down the binary size. But for anyone who likes big O notation, what you're doing there, right, is say your application has a size of 4n plus 1. And I tell you, it's amazing. We changed the 4 into a 1. But you are learned in computer science, and you tell me those are the same thing. 4n and 1n scale exactly the same. And of course, you're exactly right. The only difference between O4n and ON is that there's no difference between them, but one of them is 4 times faster, right? So I guess it's a difference of whether that makes a difference to you in the real world. But it scales the same way, and that's the point, right? So even with islands, as the application becomes larger, even if you've shrunk down to partial hydration, you're still shipping that whole thing. Now, JavaScript frameworks just do code splitting and lazy loading. So they will just split it. So you have a main bundle that loads initially, that knows how to load all these other little bundles. And then when you navigate to a new page, it will bring in the code that it needs for those new pages. We have not historically been able to do this in Rust. Rust in general, dynamic linking is a rough edge, you might say. And what we're talking about here is basically dynamic linking of a sort, right? Loading new data, but not just linking it dynamically, but actually loading code at runtime and running it. And it's somewhere where we've really struggled, where you've seen WebAssembly apps, as somebody builds up an application, that initial interactivity becomes slower and slower and slower as you add new pages to the application. And things just shouldn't be that way, right? So the compiler emits a single WebAssembly binary right now, right? Binary size scales with the size of the application, therefore the time to interactivity scales with the size of the application, and the solution is code splitting. And like I said, we haven't been able to do that traditionally with the tools that we have for Rust and WebAssembly. I take no credit for what I'm about to show you. There was somebody who did some amazing work who basically posted it, said, hey, I invented some binary splitting, code splitting for WebAssembly. I don't really have time to work on this anymore, but here's a prototype. And so we've spent a fair amount of time trying to build this into our own build tools and to try to build it into the framework, which has some aspects of the framework that are designed to work well with code splitting. So I'm going to show you this little demo. This is an amazing application, right? You load this page and you get view A, and then you click this and you get view B showing some comments. Oh no, thank you. There we go. OK, let me give it to you again. So you load the page. I have this throttled to slow 4G. You hit B. It's going to show you view B and some comments that it loaded. And then you hit view C, and it shows you, oh, there are a bunch of albums that you have. And then you go back. And OK, not a real application, obviously, right? But the point of this one is a little different from actually having an application. I want you to pay attention to some numbers for a second. So this is going to load 235 kilobytes uncompressed of WebAssembly right off the top. And then when I click view B, we're going to make two more network requests, which are for comments and deserialized comments.wasm, which is another 22 kilobytes. And then when I click view C, we're going to load two files, which are albums and viewc.wasm. So did somebody keep track of those numbers? Because I didn't. Let's go back to A, and somebody tell me the total for A is 235. Somebody hold that number in your head. And let's go into our demo and actually take out the code splitting here. So the way that this works is we have this deserialized comments.wasm, right? I've just marked that with this lazy macro. It's an async function. You notice the body doesn't actually need to be async. This is just deserializing some JSON. But we have to make it async in order to make it lazy, because the first time you call it, the code isn't there, and it's going to go and load the code from somewhere else. So if I just comment this out, who had the number? Oh, it's still here on the screen, 235. So that's no longer lazy loading. We load the application. I didn't rebuild it. I did rebuild it, but I was in the wrong demo. OK, now we sword fight, right? Yeah, OK. So 235. And then we've taken out that lazy loading. And on the initial load, we're shipping, this is small text, but can you see it, 256 kilobytes, right? So we took those 22 kilobytes that had been lazy loaded in the first example, and we just unlazy loaded them. But this means that as we add more code to the page, right, it's going to take longer and longer for this page to show up initially. And I've throttled it to 4G. You probably still couldn't even tell. The font is so big on this, it's hard to read. But this took 2.24 seconds to load. So if we put the lazy back in here, we'll see the amount go down, and let's see what the initial load time is rather than 2.25 seconds. Great. 2.12 seconds, right? So that's not bad. That's a proportional improvement. But there's also something really nice that you can see here, which is that this is just deserializing the comments. This other one in view C is loading a whole route. And this is the way you would actually tend to do this in an application, not just one function to deserialize some comments, but you would say, hey, this is a lazy route. And then what we do is we separate out the data loading part of it from the view. So this one has data, and it's going to call out to this API to get the albums that it shows. And then it has view, and it's going to show this view. And what separating out the data and the view allows you to do is something that's very nice, which is loading those two pieces concurrently. So what you end up doing is you hit this, and you'll notice, again, the small green bars, right? these are two concurrent requests, one to the API and one to the lazy loaded code. And so what you might notice is these end up, in this example, being just about the same amount of time. If you think about the fact that we're doing these concurrently, rather than lazy loading the code for this next view, which then says, oh, I need some data, and then serially loads it, right? Not only can you tuck them in next to each other, which is nice, but if you think about it, this is almost, in this particular case, a kind of zero-cost lazy loading, because when you lazy load code, of course, it makes calling that function slower, because the first time you call it, you have to load the code. But if you're lazy loading code that also needs to load some data before it can do anything useful, you actually don't pay any time cost for this. So we just save those 20 kilobytes, we save those 0.12 seconds on the initial load time, and we don't end up paying anything when we navigate to this page, because we have to go and hit the API anyway. I'm about at my time here. I want to leave a few minutes for questions. I do just want to say one thing about the final part, which is ecosystem. Ecosystem, like I said, I have a love-hate relationship. People say all the time, I would love to use X, but the ecosystem, right? When people talk about the JavaScript ecosystem that's so nice for building web applications, they're often talking about component libraries, serverless deployment platforms, animation libraries, all the sorts of amazing things that you can install off of NPM and use to build an application. When I talk about ecosystem, and when I talk about the advantages of the Rust ecosystem, I'm talking about things like cargo, cargo add, cargo test, docs.rs. Beautiful. Sirty, right? These amazing things that exist in Rust, in the language, and in the ecosystem, having exhaustive pattern matching, having result types, right? These things that can save you from yourself and let you use other people's amazing work. And it genuinely just is a question, for what you are building, is what you really need the JavaScript ecosystem with component libraries and animations and so on that you can stitch together? Or is it helpful to you to have the Rust ecosystem with all those benefits of the language that you can hear about in the rest of this conference? And genuinely, it's okay to just make a decision. I don't think I would ever recommend, I do a lot of contracting work and I maintain 4 or 5 different applications for clients that are written in 2 or 3 different JavaScript frameworks. I would never say, I'm gonna rewrite those in Rust. They're not the sort of things that benefit from Rust. I have other work that I do that really does benefit from Rust, and then I can actually create the web UI for it in Rust. So I guess my closing point there is just maybe the true ecosystem was the node modules we didn't install along the way. So is there a future for interactive Rust web applications? My answer to that is yes. I think that there is, no matter what, even if you all walk out of this room and say, oh, I'm never going to do that. But I do want to invite you to join in the work. Like I said, Leptos is just a community project. So contributions are very welcome. Getting involved is very welcome. The reason Ben is over here with stickers is because Ben was one of the first people to come into the kind of GitHub issues and Discord community and so on, and just start helping people and implementing things and making suggestions. And now he gets to work for free. So you too could do that. Thank you so much. I'm happy to take some questions. Yeah, so any questions? We have like 10 minutes, I think.
Hi, I just wanted to know, is the service splitting thing granular enough for the island thing you showed off? Like, yeah, having each individual island be split off and then loaded after the page is loaded.
Yeah, so can you use these features together? Can you use islands and lazy loading together? Yes, I'm saying confidently, not having tried it. The answer is yes. It's designed to be able to do that, right, and to have that work. I think when you're doing code splitting and lazy loading, you want to be thoughtful about how you're actually doing that. And it's one of the reasons that I did it with macro here and didn't try to do some kind of automatic version. You actually don't want to split out every possible function and then lazy load them. But for things like islands in particular, right, where maybe you have an island that only shows up below the fold, and you say, not only would I like this to be an island that's the only part of this page that hydrates, but I don't even want to load the code until I get lower down and actually need it? Absolutely. So those things are designed to work together, yep.
Hi. What do you think the role of AI is in the future of web development? And especially, it's probably been trained more on JavaScript than Leptos, for example.
That's absolutely true, yep. My experience from helping out people who have been using AI to try to build front-end things is that it can be LLMs, generative AI can be very useful for people generating at this stage, the boilerplatey parts of what they're doing. There are lots of things that lots of people have made before. And these tools can give you access to that accumulated knowledge and creation in a way that I think is helpful. I will say that the Dioxus folks have done a lot more work with like Dioxus AI and ideas of tailoring models, fine-tuning things to help you build components and so on. So they're interesting to talk to in that area. I personally, I think a little too old school, and I don't find that it's helpful in my own work in particular, and so I'm not super familiar with a lot of the tools. Yep.
This is more about WASM than Rust per se, but I have some experience with using WebAssembly with WebGL, and it wasn't fantastic like a few years ago.
What wasn't fantastic?
Mainly the time delay you got from having to do a WebAssembly call into JavaScript that then does a call into the native components of the browser. So is there any future where you can make WebAssembly calls directly to browser APIs?
Sure, great question. So the basic problem here is that WebAssembly really is just sandboxed from everything, including actual browser APIs. So not only can you not use the standard library to read a file off of someone's device, which is a good thing, but you can't call WebGL APIs, for example, directly. You have to do a byte-wise copy of data structures out of WebAssembly over into JavaScript land and then call them. So for things that are maybe shipping large amounts of data, it's definitely not optimal. Is there a world in which you can directly use those APIs? And I'll say, right, if you as a user are just using things, you use WebSys bindings and so on, you feel like you're directly calling the web APIs. Where you run into that is situations like shipping large amounts of data across that barrier and noticing some latency. Is there a world where that's possible? Yes, people have been talking about that for many years. First, it was interface types. I think as WebAssembly got more into the server and other world, people have tried to generalize some things in a way that has slowed down the process of how do you communicate with your container while trying to make it more general. So how do you communicate with the browser APIs directly got sort of subsumed into larger questions about how do you communicate with the world outside. So if you look into things like the WebAssembly component model and so on, when and if that will actually ship in browsers, who knows? 5 years ago, I would have told you, maybe in 5 years, you'll be able to do that directly. And I don't think it's any closer now than it was 5 years ago. So I would say right now, if you're doing things like shipping large numbers of bytes of data across to a web API, WebAssembly is not a good choice. For ordinary web application situations where that's not what you're doing, it could be.
Hi, I really enjoyed the talk, particularly the hot reloading part. I'm just curious, is there any, so obviously what you were changing was like the sort of DOM bit, the response. Are there any parts that you see sort of still being quite slow to compile? I mean, obviously we saw when you commented like the lazy part out that it did take a while to come back. If you change like part of the state, like the use state or anything like that, is that also quite slow or?
Sure, right.
What are still the problems with hot reloading?
Yeah, I mean, every demo is a lie, right? And so you can see it chugging away if I go back to that particular demo. Oh, I'm sorry, thank you. It's so much worse when it's a live stream and there's nobody in the room to tell me that I'm showing the wrong thing, isn't it? Yeah, good. So if you go back to this demo, here we go. If I now change something, this will still recompile. So what were we in, 3000? Yeah. So this says this will still recompile, but you can see it's still going, right? 161 milliseconds for WebAssembly, it said, it's chugging away. Okay, now it's refreshed, right? So anytime you change something, it is still going to recompile in the background. Yeah, I mean, when you're changing things that actually matter, right, where it's actually using some Rust code, let's say I stick this value in here. This, in the hot reloading, should actually show me a little, oh, it got disconnected or something, whatever. If I change this initial value, from 0 to whatever 5, right? Changing actual code, well, it's not going to do the hot reloading trick, of course, right? So yes, I mean, this is a trick, right? I don't think it's just a party trick. I do think it has actual uses, right? It actually speeds up some parts of it, but it's not at all a general purpose compile time improvement. Now we've got 5 up, right? But I was talking for a few seconds, right? Yeah.
Can you see the possibility of that improving in future? Because like even in React, there are parts of my application where if I change it outside of the component, I'll have to redo the whole thing, like the whole app reloads.
Right, because React and TypeScript are huge compiled languages, right? Yeah, so I mean, sure. I think that there are always incremental compiler improvements, and then there are lots of things that we can do. So, for example, in Leptos 0.8, that's going to be coming out sometime in the next few weeks, there are a bunch of things that contributors have done to add special dev mode. Okay, we're going to type erase a bunch of stuff that you wouldn't want to type erase in your release build, but it makes the dev build faster. So, I think what was the improvements he was saying, like 50%, reductions or something in dev mode compile times, things like that. Yeah, yeah.
Can you put the file in the hot reloaded?
Yeah.
Make the file the number in the signal hot reloadable, and we put it in the macro so it hot reloads.
Yeah, totally. And this is one of the things that the Dioxus guys have been experimenting with, right? Hot reloading any literals, right? Because it's really easy. You can just run syn over this whole thing, and syn, S-Y-N, the crate, right, will tell you, yeah, that's a literal. And now it's a different literal. What can you do with that information, right? There are definitely things that one can do. There are things that I haven't done, so I can't show them to you right now. Yeah. Any other questions?
You mentioned having to get the standard library through the WebAssembly.
Yeah.
So in the case of if I have a page B, would I first need to get page A if page B was code split out in order to load the standard library in?
Yeah, you're talking about the code splitting examples, right?
Yeah.
In the code splitting example, this example is actually a little too simple to show this off. The code to do the code splitting analyzes WASM files, and it will actually pull out shared dependencies between. So for example, if view B and view C here were both lazy loaded and they shared some function, there will be a model that's view B, view C, a module that's view B, and a module that's view C. And so the first time it loads view B, it will load view B and view B, view C. And then when it loads view C, it will just load view C. If you do it the other way around, view C will load view B, view C, and view C. And then if you click on B, it will just load B. And then obviously this is lazy but not stupid loading, right? So if you navigate back to the page, it doesn't lazy load it again. It already has the code. But so there are, as far as the standard library, yeah, I mean, there are things that will end up in the main bundle that are used on all pages. There are things that will end up in shared between 2 pages or something. But also, like, let's be honest, right? Rust is an amazing language. The fact that I'm saying, yeah, well, it has to ship the standard library, right? And, okay, this is one of the island examples, but the kind of minimal size you get is like, yeah, 44 kilobytes, right? I mean, to be shipping that level of functionality, it's already actually amazing. I will say, right, we're sitting here saying, oh yeah, 44 kilobytes, that's big. You don't get this in other languages. Like there are projects to compile other languages, Go, Kotlin, and so on, to WebAssembly. You don't get a 45 kilobyte file. If you've ever used Blazor, has anyone used Blazor? C#, yeah. I mean, you're shipping like 950 megabytes of WebAssembly, right? The whole C language runtime, right? So I'm sorry, that's probably unfair. I don't actually, whatever. But this is actually an amazing thing that Rust can do, even while we try to improve it.
It's also build standard, right?
Yes. You can on nightly. You can tell. So we're always using by default release builds are with opt level 3, which is make it really fast and as big as you want. And in web context, you often want opt level Z, which is make it really small, even if it makes it marginally slower to do something. And so on nightly, you can rebuild the standard library with your actual cargo toml profile release settings. So you can get some pretty big, these are all built that way, 30, 40 kilobyte reductions by just compiling with different settings for the standard library. Yeah.
Does the code splitting take into account when you stream, when you stop on the page, like you've got an infinite stream key, and it adds some chunks
Well, so those are three separate questions. So one is about streaming and infinite scroll, which yes, you can do. One is about if you had streaming with infinite scroll and an island popped up on the page subsequently, would it get hydrated? And yes, you can do that. And then the third question is, when you do that, could that code to hydrate that island be lazily loaded? And yes, you can also do that. And when I say yes, you can do that, I don't mean if you open your laptop and say, Greg, show me how to do it. You can do it right now, but these are things that are very easily achievable within the paradigm we're talking about. Yep. Thank you all so much. I think we're at time. I'm happy to chat. Yeah. Thank you.